Hello, this is Honors Algebra 2, and we're going to be doing the notes on radicals, how to simplify them. What does it mean to be simplified? Now, when you take a quiz on this particular concept, you will not be allowed to use this calculator, and I know many of you have this one. So maybe see if you can borrow a different calculator. Or if you have this calculator, bring this one along with you. Put it in your bag if you don't have it in your bag already. So you'll be allowed to use this calculator on your quiz, just not the other one. Okay. An expression with radicals, meaning square roots, cubed roots, etc., is in its simplest form if the following three things are true. I look at this example, the square root of 8. The 8 underneath the radical sign is called the radicand, and no radicands have perfect square factors other than 1. Okay, now understand what a perfect square is. If you have a square, all 4 sides are equal in length. And so if you have a square whose side lengths are 2, the area of that square would be 4. Because you have a 2 by 2, and when you find the area, it's length times width, or base times height. And you get an area of 4. So 4 is a square. Now we're going to look at the factors of 8. Now remember, factor, it does mean divide. So factors of 8, or the numbers that divide 8, would be 1, 2, 3 doesn't, 4 does, 5, 6, and 7 do not, but 8 does. And if you look here, 4 is a perfect square. And so radical 8 is not in its simplest form. And we're going to learn how to simplify that. Hopefully you have already seen this in some math class. Hopefully you saw it in geometry. The next thing is no radicand can be a fraction. So I see this, the square root of 3 over 4. I have to break that apart, and I have to simplify the denominator. Because the third thing is no radicals appear in the denominator of a fraction. So all 3 elements in my examples column are not radical expressions in its simplest form. Okay, so we're going to work through, figure out how we simplify these. In the following 2 properties of radicals are useful in helping us to simplify a radical expression. You have to let a and b be positive numbers, especially for your even root radicals, because you can't take the square root of a negative number. There is no number whose square would ever be negative. In other words, negative 2, if you square that, you get positive 4. So the square root of a product meaning multiplication, equals the product of the square roots of the factors. In other words, I look here at my example and I see the square root of a times b. I can break this apart into the square root of a times the square root of b using the product property. So a couple of examples to prove to you that it works. If I have something like the square root of 16 times 4. I can multiply 16 and 4, but I'm going to get a bigger number. And although this number is not that big, sometimes they do get quite large. So you're going to want to simplify this in easier steps, if you will. So if I use the product property, I can break this apart into the square root of 16 times the square root of 4. Of course, the square root of 16 is 4. The square root of 4 is 2. And I see this thing equals 8. Now, had I just left it, square root of 16 times 4, and said, well, that's the square root of 64, I'd get the same answer of 8. So that's why the product property works. But again, sometimes these numbers are big. You know, this could be a 25 and this could be a 6. You don't want to multiply that together and then try to simplify it later. And because multiplication and division are inverses of one another, we also have a quotient property, the square root of a quotient. Now remember, when you divide, the result of a division problem is called a quotient. And so that's why this is called a quotient property. Same sort of thing happens. Instead of saying the square root of the fraction a over b, we can split this apart and write it as the square root of a over the square root of b. Again, we'll use the same two numbers to show you that it works. Square root of 16 over 4 equals root 16 over root 4. Now remember, when you take the square root, the radical symbol goes away. All right, the square root of 16 is 4. And the square root of 4 is 2. And 4 divided by 2 is 2. Had I just divided, keep in mind, these are not always going to divide. And that's why we learn these properties. This becomes, well, 16 over 4 is 4. This becomes the square root of 4, which equals 2. So you get the same answer. And it really helps if you know your squares. And I recommend that you memorize 1 squared, 2 squared, 3 squared, 4 squared, all the way up to 20, and then of course number 25. 25 squared is 625. So that would be some common knowledge that you should acquire if you don't already have that knowledge. It's called your multiplication facts. All right, side 2. We're going to talk about the ladder method. I call it the ladder method because I have this list which looks like a long ladder, and I can go up the ladder. Okay, so when we're trying to break down the radicand into two factors where one is a perfect square, you want to find the two squares that the given radicand falls in between. So, in other words, if I look at my first example, simplify the square root of 98. Well, I'm going to look at my list, which I have to fill in. And I'm going to look for what two squares in my list that 98 falls in between. And I'm going to work my way up the ladder to figure out which square, if any, divides 98. So it says, work your way up the ladder by dividing your radicand by each square. If no square divides the radicand, then the radical is in simplest form. The number underneath the radical symbol is called a radicand. And when we fill in this list, we're going to say the radicands in the list are all perfect squares. All right, so the best thing we could do here now is to complete our list. All right, the square root of 1 equals 1. Why? Because 1 squared equals 1. The square root of 4 is 2, because 2 squared is 4. The square root of 9 is 3. Why? Because 3 squared is 9. Now we're not going to use positive and negative here because the sign in front of all these radicals is positive. We're looking at the positive case only. So we can fill this part in 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and 25. Because remember, I want you to know your squares from 1 to 20, and then number 25. All right, let's work backwards now. The square root of what is 4? Well, the square root of 16 is 4 because 4 squared is 16. 16 is my square. It's a 4 by 4. 5 squared, 25. 6 squared, 36. 7 squared, 49. 8 squared, 64. 9 squared, 81. 10 squared, 100. 11 squared, 121. I always say there's 2 1s, so I shove a 2 in between and I get 121. 12 squared, that should be one that's pretty common for you, 144. 13 squared is 169. And 14 squared, you transpose the 6 and the 9, you get a 196. 15 squared, folks, this ends in a 5. I'm going to do 5 times 5. If I would do long multiplication, so that's 225. 16 squared is 256. Has to end in a 6, right? If I would do 16 times 16, 6 times 6 is 36. It ends in a 6. This one has to end in a 9, right? 7 times 7, 49. And in fact, it's 289. This one's got to end in a 1. I mean a 4, rather. 8 times 8 is 64. That's 324. 9 times 9 is 81. This one ends in a 1. That's 361. 20 squared, that should be easy. That's 400. And 25 squared is 625. So it would behoove you to memorize those squares. It's going to make the task of simplifying radicals so much easier because you'll be able to recognize certain numbers as perfect squares. Now, let's look at our first example again. 98. 98 is between what two squares? Well, 98 is not 100, but it's not 81, so it's in between here. So all these other ones, I don't care about them. I'm going to work my way up the ladder. Does 81 divide 98? No. Does 64 divide 98? No. You could try it on the calculator. Does 49 divide 98? Yes. It divides it 2 times. And so the square root of 98 can be rewritten as the square root of 49, the square, times 2. I'm going to use the product rule that says square root of 49 times 2 is the same as the square root of 49 times the square root of 2. Simplifying, the square root of 49 equals 7. The square root of 2 is an irrational number, and it's not a perfect square. That radicand is not a square, so I simply say this now equals 7 times the square root of 2. You can check this on the calculator. If I type in the square root of 98, I get a decimal. And that's because square root of 98 is an irrational number. So you're going to get a decimal. You can't change it to a fraction because it's an irrational number. And then I could do 7 times the square root of 2. And you should get the same exact decimal. That's because those numbers are equal to each other. They just look different. Another way that you can use the ladder method is take your radicand and first divide it by 2. You know, cut it in half, especially if it's even. If it's odd, don't divide by 2. But if it's an even number, you know, you could say 98 divided by 2 is 49. And hey, 49 is a square. So now I've got my two factors of 98, and one of them is a square. Okay, and then I can go right to this. It's up to you how you want to do that. 200. 200 is not a square. Where does 200 lie between? Well, it lies between 196 and 225. So these do not apply. I can go up the ladder. This won't divide, that won't divide, that won't divide, that won't divide. But 100 does divide 200. It divides it 2 times. You could have said, well, 200 is even, so I could do 200 divided by 2 and get 100, and 100 is my square. So I could rewrite this as 100 times 2. Now, what I like to do so that I don't have to take so much time and write this out and actually show the product rule, I like to circle my squares and then draw an arrow and show it comes out, right? Because the square root of 100 is 10. This has to stay in because it's not a square. And so this simplifies into 10 times the square root of 2. Now, we're going to look at 40. 40 is not a square. It's even. All right, let's do 40 divided by 2. I get 20. Is 20 a square? If you look in your list, it's not a square. It's between 16 and 25. Well, I could try then to divide by 3 if that didn't work. Well, 40 is even, 3 is odd. I'm going to get a decimal. I don't want to do that. The next even number is 4, and 40 divided by 4 is 10. Now, while 10 is not a square, guess what? 4 is. And so I'm going to take 40 and rewrite it as 4 times 10. You see, because we are looking for numbers that divide the radicand that are perfect squares themselves. So I circle the 4. I show that it's going to come out as a 2. Why? Because the square root of 4 is 2. The 10 stays in. Okay, this came out. What's left? I'm going to cover that up. I still have the square root of 10. So this is going to simplify as the 2 times the square root of 10. 10 has no factors other than 1 that are squares. 75. Some numbers are easy to figure out what the square is, if they're small enough. I look at 75 and I see 25 divides it. I know it divides it 3 times. 25 is my square. It comes out as a 5. And so this simplifies as 5 times the square root of 3. 32. 32 is not a square. Let's look on my ladder. 32 is between 25 and 36. 25 doesn't divide it, but does 16. 16 does divide 32 twice. So you could either do 32 times 2 and get the 16, or you can go up the ladder. This one is 16 times 2. The 16 comes out as a 4. And so this simplifies as 4 times the square root of 2. Okay, so on a test or a quiz, you are going to have to show me this work right here. You can't just, put an answer down. And you can't use that one calculator I told you about. All right, 288. Well, you could bust 288 in half. What do you get? 144. So guess what? 144 is a square. So I'm going to rewrite this as 144 times 2 equals 144 comes out as a 12. And so this one simplifies as 12 times the square root of 2. Not too bad, not too terrible, I don't think. Now, in the future, we're going to introduce variables, and you're going to have to simplify and take out squares on your variables, like x squared, x cubed, x to the 5th. And so you might want to think of that and those in terms of a factor tree. So this second page of notes is going to be just that. So simplifying radicals notes continued. The prime factors method. Okay, you're going to write the radicand as a product, again, like we just did. But you're going to write it as a product of all of its prime factors, like a factor tree. Recall a factor tree for the number like 24. Well, 24 is even, so 2 divides it. 2 divides it 12 times. It would be 12 times 2. That equals 24. We can break the 12 down into 2 times 6. But this 2 has to come down, okay, to the bottom row. Because it's 2 times 2 times 6 that equals 24. 6 is still even. That's not a prime number. This 2 comes down. This 2 comes down. This 6 can be broken into 2 times 3. Now I have prime numbers in the bottom row. Those are the prime factors of 24. Okay, these are all prime. So we can look at this and say 24 is exactly equal to 2 cubed times 3. Yes, 2 cubed. 2 times 2 times 2 would be 2 to the power of 3. Okay, so simplifying the radicals helps you with some number theory and thinking about numbers in a different way. Go through the list of prime factors that you just wrote down. Groups of 2 are removed from the inside of the radical. Why? Because, here's a group of 2, 2 2's. That would be 2 squared. 2 squared is 4, and 4 is the square that would come out. So we're looking for groups of 2 that are the same. Okay, so in this example above, I only have one group of 2. This 2 and this 3 would have to stay inside the radical if there was a radical around this. Okay, so groups of 2 are removed from the inside of the radical and are written on the outside. And you're going to write it not twice on the outside. You have to write it once. Right? 2 2's on the inside, so if I go over here on the side, the square root of 2 times 2 would be equal to 2. Okay, groups of 2 come out as once. Why? Because 2 times 2 is 4, and the square root of 4 is 2. If there are 2 or more factors moved to the outside, then you need to multiply them together. If there are 2 or more factors remaining on the inside, you have to multiply those as well. So if this had a square root around it, these 2 would come out as a single 2, and then I would have to multiply the 2 and the 3 on the inside to get a 6. So the square root of 24 would simplify as 2 times the square root of 6. All right, a little bit of review. 1 equals 1 times 1, so the square root of 1 is 1. 4 could be written as 2 times 2. A group of 2's comes out as a single. Square root of 4 is 2. This is just to illustrate to you that this works. 9 is 3 times 3. I have a group of 2 3's. That comes out as a single 3. We know the square root of 9 is 3. Same thing with a 16. That's a 4 times 4. So the square root of 16 is 4. 25, 5 times 5. One group of 2 5's comes out as a single 5. Root 25 equals 5. 36, 6 times 6. So root 36 is 6. 81, 9 times 9. So root 81 equals 9. 225 is 15 times 15. And so the square root of 225 is 15. Okay, this was just meant in here for practice so that you start learning your squares. Okay, so we have a few more examples to do, and then we are finished with this part of the lesson. Simplify the radical expressions. Use the product and the quotient rules if needed. 50. I look at 50 and I see a 25. I could cut 50 in half and get 25. Now I recognize 25 as a square. So I'm going to rewrite this as root 25 times 2. The 25 comes out as a 5. So this is going to simplify as 5 times the square root of 2. Now, I could have taken 50 and busting it down to its prime factors, okay? Root 50 equals 2 times 25. Don't forget about the root. Break down the 25. 2 times 5 times 5. I have a group of 2 5s. It would come out as a single 5. I got the same answer, 5 root 2. And we can squish that on here. Okay, so, it's up to you if you want to use the ladder method and look for larger perfect squares, or if you want to use this, break it down to its prime factors. All right, this one, we're going to use the quotient rule. This is the square root of 5 over the square root of 16. Square root of 16 is 4. I mean, you could write it as 4 times 4 and show a group of 2 come out as 1. But I'm fine if you know root 16 equals 4, and you just go right to that. 5 has no square factors. 5 is prime. 24 and 36. Well, the top is root 24. The bottom is root 36. The bottom is a 6. 24. You could use your calculator to help you. You could do 24 divided by 2, even divided by 2, even divided by 2, odd. So 24 is 2 times 2 times 2 times 3. Okay, so use your calculator to help you. If you don't have one of these where it saves some stuff on the screen for you, you don't have a graphic calculator, then you might want to have a sheet of paper and just keep writing it down. In other words, if you do 24 divided by 2 on a calculator and you got a whole number, you would write the 2, then do it again, write it down again, then do it again, write it down again. And then once you get to an odd number or a prime number, write the 3 down. All right. This pair of 2's comes out as a 2. So I've got 2 on the outside in the numerator. 6 is in the bottom. Now I have to multiply 2 times 3. I can't just leave it like that. That's times the square root of 6. Now, keep in mind, you cannot divide these 6's because this is inside a radical and this is outside a radical. So they cannot be divided. But since these are both outside, I can simplify this, and you must simplify this. 2 divides 2 one time, 2 divides 6 3 times. And so my final answer here is the square root of 6 divided by 3. Okay, 400. Well, if you know 400 is a square, then just bam, write the answer. Or do 100 times 4. You could break it down to its prime factors. I don't think it's necessary. The square root of 100 is 10. The square root of 4 is 2. What do you do with the outside ones? You multiply. There's nothing inside except a 1. Well, 1's not a prime number. We spoke about that. The square root of 1 is 1. So this would be 10 times 2 times 1. Or 20. But again, if you knew 400 was a square, you could, bam, go right to the answer. 2 more. Oh, multiplication. Well, folks, multiplication is commutative, meaning we can move things around. So 2 times the square root of 3 times 5 times the square root of 6 is the same as 2 times 5 times the square root of 3 times the square root of 6. All right, well, I can multiply the 2 and the 5 because they're both on the outside. That's 10. 6 times 3 is 18. And you can do this one of two ways. 18 is, we'll do this here. This is the square root of 18. And 18 is 9 times 2. So you could go right to the 9 times 2 here. Or you could write 3 times 2 is 6. 3 times 2. You see, this 3 is that 3, and this 3 times 2 is that 6. I've got a pair of 3's that come out. That's a single 3. Now that's on the outside, and so is the 10. You have to multiply them. That's 30 times the square root of 2. Again, if you wanted to treat this as 9 times 2, the 9 would come out as a 3 anyway. So it depends just which way you see the numbers and what you're more comfortable with. This one here, 2 root 3 raised to the second power. Well, this really means 2 root 3 times itself 2 root 3, right? The exponent tells us how many times they're being multiplied together. This is 2 times. So I could rearrange, this is 2 times 2 times, since they're both inside a radical, I'm going to write it as they're both inside the radical. 2 times 2 is 4. Root 3, 3 times 3 would be 9, or a pair of 3's comes out as a 3, right? So this is 4 times 3 for a final answer of 12. So, if you have any questions on these, post a comment or ask a question in class. Again, this takes a little bit of concentration. You have to know your math facts. And I don't know what to say. If you're struggling with it, then you need to ask for a Google Meet, ask questions in class, and I will be more than happy to help you. Have a great day.